So this is the second question today we will solve. So let's read the question at first and try to understand. So it is a hot carbon dioxide exhaust gas which is at 1 atm pressure is being cooled by the flat plates. So this is our interest actually, what it is, whether it is flat or the vertical plate or cylinder, whatever it is. So what we got is what carbon dioxide gas is being cooled by the flat plate. So initially the gas was 220 degrees centigrade temperature, flows in parallel. So this is another keyword. So the first thing is it is the flat plate, and now the gas it is flowing parallel over the upper and the lower surfaces of 1.5 meter long flat plate. Okay, so what you got so far, what carbon dioxide gas is being cooled by the flat plates. Initial temperature was 220 degrees centigrade, and the gas is flowing parallelly over the upper and the lower surface of the plate, which is 1.5 meter long, and the velocity, the free stream velocity, is 3 meters per second. Alright, so if the plate surface temperature is maintained at constant 80 degrees centigrade temperature, so you have to calculate the local convection heat transfer coefficients at 1 meter from the leading edge, the average convection heat transfer coefficients for the entire plate, and the total heat transfer. So let's say this is the flat plate, and the hot carbon dioxide gas, it is initially 220 degrees centigrade, it is flowing this way, okay, and the velocity, free stream velocity, is 3 meters per second. So this is the free stream velocity. The surface temperature of the the long flat plate, it is 80 degrees centigrade. So this is 80 degrees centigrade, and this flat plate, it is 1.5 meter long. Okay, so the total length, the entire length of this plate is 1.5 meter long. Alright, so and initially the gas is 220 degrees centigrade temperature. This is 220 degrees centigrade temperature is flowing at this temperature. So that means the gas temperature is higher and the flat plate temperature is lower. So he is actually the donor, isn't it? This flat plate will gain some temperature from here, and by that way the word carbon dioxide gas will be cooled. Okay, so this flat plate, it will gain the temperature. Alright, so the first part of discussion is what will be the local convection heat transfer coefficient at 1 meter from the leading edge. So as you know, I said when I solved the first question or during my lecture, this is actually the leading edge. Okay, so the starting of the plate, this is the leading edge and this is the trailing edge. So let's say the distance from the leading edge to 1 meter, let's say this is, if it is 1.5 meters, so you can say, okay, this is 0.5, this is 0.5, this is 0.5, just roughly. So that means this whole distance is 1.5. We can say, okay, this is up to this point, this is 1 meter. Okay, from here to here it is 1 meter. So we have to calculate what will be the local convection heat transfer coefficients, okay, at these states at 1 meter from the leading edge. And second thing is for the entire plate, that means for 1.5 meter. So as usual, when we solve any heat transfer problem, I said we'll write down some assumptions. Why assumptions important here, guys? In reality, if it is 1.5 meter long pipe, maybe the surface temperature of the plate will not be uniform, maybe some variations throughout the surface. But when we will consider the real aspects, it's nearly impossible to solve this phenomenon by using some analytical equations or mathematical expressions. So what we do, we just try to make it simple and we say, okay, let's assume the surface temperature is constant. That's easier because we need other properties. So if the temperature here is different, here is different, if constantly change, then the properties for those temperature will also be different. So this will make our life, you know, complex. So what I said, okay, when we'll solve any problem, any heat transfer problem, we will try to make this problem as simple as possible. So we'll write some assumptions. So here you will see we have some assumptions. We will consider this system is steady. So we'll say that okay, steady operating conditions exist here. The surface temperature throughout the plate for 1.5 meter, we'll say this is constant. So it is uniform. It's not changing. It's just constant and 80 degrees centigrade. So for this uniform temperature, we said the thermal properties, this is also constant because the surface temperature is not changing. So the thermal properties will not change as well. And in this case, we are not considering any radiation effects. So we will neglect that radiation effects. And you see, actually the convection will happen here because we have this solid object and the gas, so the heat transfer happening. You already know what is convection and what is conduction. So we say the radiation effects are negligible. So now we need to calculate the properties. We already discussed about the properties, that how to calculate the properties. So what we will do, we will calculate the film temperature. I discussed earlier why we need the film temperature. So in this case, the film temperature formula is the surface temperature and the atmospheric temperature. This just the arithmetic mean of the surface temperature and the the atmospheric temperature. 220, this is actually the atmospheric temperature, T infinity. And this 80, this is actually the surface temperature. And this is just the arithmetic mean, that means over 2. So it should be 150. You will see guys here, the gas is carbon dioxide. So at 150 degrees centigrade temperature, the properties of carbon dioxide, this is from your book, table A16. So we need the thermal conductivity, K. Nu, this is the kinematic viscosity, and the Prandtl number, because Prandtl number is the function of the Nusselt number. When you have some correlations from benchmark experimental data, you will see Prandtl number is just the function of Nusselt number. So we need the Prandtl number, yes. So the first question is, what will be the local convection heat transfer coefficient here? Haze. So if we want to get haze, look guys, see here, if we actually need haze, that means we all know this convection heat transfer coefficient, it is function of the Nusselt number, because Nusselt number formula, it is haze L over K. So that means if we need this haze, then if we calculate the Nusselt number, then we will get haze from there. But if you actually want to calculate the Nusselt number, then you need to know whether your flow is laminar or turbulent, because for laminar flow, the Nusselt number expression will be different. For turbulent flow, it will be different. So that means you need to know before calculating the Nusselt number, your flow is laminar or not, or turbulent or not. So how you can do that? To do that, you need to calculate your Reynolds number. So calculate your Reynolds number and see whether it is greater than or below the critical Reynolds number and decide whether your flow is laminar or turbulent. So then you have done. So that means this is the overall flow jet. We are going to follow this problem, especially for the first part of this problem. So at first we will calculate the Reynolds number, we will calculate the Nusselt number from the correlation, and then we will write down that value is equal to Hayes L and K. L, the distance 1 meter, thermal conductivity we know from the properties, then we will get Hayes. And there's the first part of this question. So let's go. So the Reynolds number at x equal 1 meter, because we are calculating the local convection heat transfer coefficient at this distance. So we said this is actually the local Reynolds number. So we said Rex equal Vx and nu. You know this formula. So the velocity 3 meter per second, x is 1 meter, the distance, and the kinematic viscosity is constant from the properties. So we got the the Reynolds number, and you can see clearly it is 1.8 and 10 to the power 5. So we know the critical Reynolds number is 5 into 10 to the power 5. If your Reynolds number is this or greater than this, then flow will be turbulent. Here we can see it is 1.844. So it is clearly just less than that value, the critical Reynolds number. So the flow is laminar. Alright, so when the flow is laminar, then we need to select the Nusselt number correlations for laminar flow. So the heat transfer coefficient we will calculate, but we know the Nusselt number correlation NUX for laminar flow it is 0.332, the Reynolds number and power half, and the Prandtl number 1.3. So this is actually the Nusselt number correlations we know from the experimental data. It is given in your book. People already developed this correlation, and now we are using these correlations. That's all of these correlations we got from some benchmark experiment, and that's accurate. So now you substitute the values for Reynolds number. So it is 1.884 and 10 to the power 5, and we calculated the Prandtl's number from the table. So we got the Nusselt number is 129.2. So this is the Nusselt number value. And now from the definition we know Nusselt number equal Hayes L and K. So substitute the Nusselt number equal Hayes and L. Instead of L we said X. So it's same thing, X and L, it doesn't matter. So you can say this is L as well. Over the thermal conductivity it is equal to 129.2. So that means if you solve this on for Hayes X, it will be 129 into thermal conductivity over the distance. So substitute that value, and the distance is x1. So the Hayes X will get the local convection heat transfer coefficient is 3.426 at x equal 1 meter distance from the leading edge. So that's the first part of this question. I believe you understand this because we solved a similar problem earlier. So you all know how to calculate the convection heat transfer coefficient, but here we calculated the local convection heat transfer coefficient at x distance. The second part of this question is we need to calculate the average convection heat transfer coefficient. So we will calculate the average convection heat transfer coefficients for over the entire plate. The entire plate means for 1.5 meter length. So that means this is the total length for this flat plate. And finally we will calculate the heat flask. This is the last part of this question. So when it was for local convection heat transfer coefficient, we used X. So now for the entire plate, that means 1.5 meter, we calculated the Reynolds number again. It is 3, the velocity 1.5 meter is the distance, and this is the kinematic viscosity. So once we use these values, then we got the Reynolds number is 2.766 and 10 to the power 5. So this is less than 5 in 10 to the power 5, isn't it? So that means the flow is still laminar for this plate, 1.5 meter long plate. But if you can remember, now you may, some of you may ask me, okay, the flow is laminar. We calculated Reynolds number. We can say it is less than critical Reynolds number. So flow is laminar. Why you are using a different Nusselt number correlations here? Why you are using this? Because previously you used the Nusselt number is 0.332, Reynolds number 0.5, Reynolds number 1.3. But here, why you are using it's 0.0664? Why not 0.332? Yeah, that's a good question. So the thing is, when we calculated this Nusselt number at x equal 1, it was local Nusselt number at x equal 1. And for local values, we have these correlations. But now we are calculating for the entire plate, for the whole plate, and this is not local. This is the average Nusselt number for the entire plate. So for average Nusselt number, we got different correlations. So that's why we're using this correlation here. And I believe now you understand why I'm using this one. So we substitute the values for Reynolds number that we calculated, and we substitute the values for the Prandtl number. So once I did that, then we got the Nusselt number is 316.5. Same thing, we write it down like Nusselt number equal Hayes LK. L here it is for the whole length, the entire length 1.5 meter. So we solved this expression, this Nusselt number expressions for Hayes, the convection heat transfer coefficient, average convection heat transfer coefficients for the entire plate, and we got it is 5.596. So this is the second part of this question. Now we will calculate the third part. Let's say this is C. Okay. So the third part of this question, we need to calculate the heat flask. Just have a look the question here. It is flowing over the upper and the lower surfaces. Okay, the upper and the lower surfaces. So we will calculate the total heat flask, the flat plate on the upper and the lower surfaces. Alright. So now this is, the convection heat transfer is happening here, and from convection heat transfer we know actually the heat transfer, the rate of heat transfer, it is equal the convection heat transfer coefficient, the surface area, and delta T. So this is we know from the formula. But you can see guys here what I did, I wrote it 2 Hayes delta T. Delta T is the temperature difference from high temperature to low temperature. So this is actually delta T Hayes. Where is A? So we know for convection heat transfer coefficient, the rate of heat transfer during convection, the formula is this. So we have here Hayes and the delta T. We do not have A here. And again, we wrote it 2. Why? So the thing is, we are calculating the heat flask. Heat flask is actually when you will calculate, so definitely I'm not going to discuss the theories, but let's say, when you will calculate the heat flask, you need to, calculate for per unit area. So you need to divide by the area. So this area and this area will cancel out. So heat flask is It is just haze delta T. So the heat transfer coefficient and the temperature difference. Now you can ask me, okay, we understand why it is haze delta T, why A is not here, but why you are using this too? You can see we are calculating for the upper surface and for the lower surface, so both surfaces 8 plus, so we multiply it by 2 because we are calculating for the upper and the lower surface. So this upper, this lower, so you say 1 plus 1, 2 different surfaces, so we just multiply it by 2 because yeah. So now haze equal this, and the temperature difference is this, so we got the rate of heat transfer. This heat flask is 1567. So that's it. So now your task is, we calculated this problem, but the entire plate, the flow was laminar. If we have a plate sufficiently long enough to become turbulent, so let's say up to this section this is laminar, maybe this is now 5 meter long, so the flow could be turbulent here. So what will happen if you have a problem where the flow is both laminar and turbulent? That means if you see the mixed boundary there, what will happen? Try to find out some questions, something like that, and practice it. So that's all.